So let's get to it. Let's have a good look at our algorithm. And I have taken out again the verbose port and so on, so that it's a little bit easier to see. And here we have it. So in this algorithm, I first of all have a for loop. Okay, that goes all the length of my list. All the length, you will say, well, all the length but one element. Okay, and as you remember from last time, the additive constants, in this case 1, do not really matter. Okay, so I'm going to consider that I have an n type complexity here, which I do in this list, in this loop. Okay, what am I doing inside of my loop? We saw that if I have a n complexity loop that has something constant inside of it, then all the cost is linear, is O of n in total. And if I have a loop that has something that's linear inside of it, then all the cost is quadratic. Okay, what happens in this case? Well, first of all, I have these assignment operations, which are simply constant, as all atomic and general operations are. Okay, as long as I'm not calling any function that might have complex things on it, most things are just constant, as happens here. I also have something that's constant here, the comments are constant, the assignation here is also constant. And what else do I have? Well, I have a loop inside of this. Okay, so now I have to be very careful because this is a while loop, it's a search loop, so I cannot automatically say that this is going to be linear. I have to look at it. Okay. Okay. How many times does this loop run? Well, I start at pause and I end up when pause is bigger than 0 or when I find an element that's not bigger than my current element. Okay, so I'm going to be checking all the elements from pause down to 0 until I find one that's not bigger than my current element. How many times does this run? Well, if I'm lucky, like in the first iteration of the example that I saw, my element might already be in its correct position, and I won't need to even enter the loop. I will see that the previous element is not bigger than this one, so I'm done. Okay, but if I'm unlucky, I might need to go down all the way to the start of the list, like we saw in two cases. The last one, when I had to move an element that contained 1 all the way to the first position of the list. Okay, so how many times does this loop run? Well, it depends, but as I said before, worst case scenario is what we consider in these cases. So I'm doing worst case scenario complexity, and the worst case scenario for this loop is running all the length of the list. Okay, from my current position to 0, and I can be as big as the length of the whole list. So this loop can run as many times as n times, and that's what I'm going to consider this complexity. So I have a loop that runs n times inside of a loop that runs n times. So my complexity is at least quadratic. But I need to see what happens inside of my second loop, because if I have another loop inside of here, my complexity might be bigger. But I don't. What happens inside here is all constant. Okay, I have two assignments and some arithmetic operations. So I have a linear type of loop because with constant contents, so all of the loop is linear. So then I have a linear loop with something that's linear inside of it. The complexity of my function is quadratic. It's the same case that we saw for the counting of repeat occurrences of elements. And in this case, I have a double loop, both with linear worst time complexity. So the complexity of insertion sort is n to the squared. Okay, and you have a little bit of a longer explanation here. To finish this session, is this optimal? Remember optimal? What does optimal even mean? It means whether or not the complexity of the algorithm that I have just seen is the best that I can get to solve my problem. There are many algorithms to solve one particular problem, and the complexity of the problem is the complexity of the fastest algorithm that solves the problem. Insertion sort solves the sorting problem, so if there is no better way to do that than quadratic, if there is no algorithm that's faster than quadratic, then insertion sort is going to be optimal. And I'm not going to give a demonstration here, but I'm going to give a strong intuition. Okay, I'm going to compare insertion sort to all good Python sort. Okay, and I'm going to do the same that I did before. I'm going to generate lists of growing length, and I'm going to generate one and copy it, and then I'm going to measure the time to compute insertion sort and Python's sort algorithm, and I'm going to compare them. Insertion sort has again a very pretty quadratic tendency. Python sort has a bit of a more complicated tendency, which I would call more towards linear, and we will see that's not really linear, but not today. We will see it in a further session. And when I compare the two of them, I get that insertion sort is way slower than Python's sort function. Okay? So even though I haven't proven it, it really does not look like insertion sort is optimal, because this tendency looks slower. This tendency looks slower than this one. Okay, so it's very likely that Python's sort algorithm has a different type of complexity, a smaller complexity class, a faster complexity class, so insertion sort is not optimal. I haven't given a proof, but I have given a pretty strong intuition with this. You might want to look ahead and check what the complexity of insertion sort is. But so far, for this session, that's it. Next session, we will be speaking about recursive algorithms, and we will be introducing other complexity classes. So far, we have been seeing examples of linear complexity, constant complexity, quadratic complexity, and we have introduced the sorting problem and our first sorting algorithm, and there are more that you can check. And next time we will speak a little bit about recursivity, which is a very useful programming technique, and we will be giving many more examples of algorithm complexity.